We now know how to plan a flight for a small aircraft or a big jet aircraft, whether that be flying VFR or IFR. But how do we use this plan when we're actually in the air? And how do we make contingency plans should we need them if things start to deviate a bit from that flight plan? Let's find out. Hi, I'm Grant and welcome to the 8th class in the flight planning series. Today we're going to be taking a look at how to actually use that flight plan whilst we're in the air to monitor our flight progress. We're also going to have a look at a few contingency procedures. These are things that we might use to help us make a decision if things start to deviate from that plan that we spent such a long time making on the ground. These are quite a useful thing to have in your back pocket because it means that if push comes to shove and you actually have to make a decision such as turning back or diverting, you already have done a lot of the work on the ground and it's a very simple call for you when you're in the air focusing on all the other stuff such as flying and air traffic control and navigating and that kind of thing. During the flight we obviously burn fuel, but we need to be sure we are burning the correct amount for that phase of flight. We also need to make sure we arrive at our destination with enough fuel so we are safely able to make an approach, possibly go around and divert to an alternate with the final reserve still intact. At the start of the day, we will put on sufficient fuel to meet the legal limits, which basically breaks down into the various components of taxi, trip, cafe. Quite often, we come up for figures for these different amounts of fuel required and come up with a total amount in kilograms or pounds, the weight of it. This is because we like having the weight of fuel rather than the volume for use in mass and balance calculations. The fuel truck that is giving us the fuel will usually read an output of fuel in terms of litres or gallons. This means we might need to convert between the two so that the fuel truck knows the correct amount that's going into our tanks and it matches the weight that we want of fuel and we get the correct amount on board. As a rough rule of thumb, Jet A1, which is the standard fuel for jet aircraft, weighs about 0.8 kilograms per litre, but this can fluctuate slightly with temperature. So let's say we calculated that our block fuel, our fuel for this sector, was 8,000 kilograms. Then we would say that we want 10,000 litres to the fuel truck. Or they might do the calculation for us. If we say 8,000 kgs, they go, right, I know that my truck delivers in litres. We're going to use 0.8 as the specific gravity, so I'll put on 10,000 litres. You basically just have to be aware of the units that your aircraft use and the fuel truck use so that you don't get confused or the fueler doesn't get confused. In Europe, the metric system is king, so it's pretty much always litres and kilograms. But in the United States and other countries, it might be gallons and pounds, for instance. And there's actually quite a famous incident where Air Canada Flight 143 used the wrong units because the company had recently changed from the old imperial system to the metric system. And this basically meant that they ran out of fuel mid-flight. Hence the importance of monitoring the fuel even before we've left the ground or left the stand. Once we have loaded the correct amount of fuel and we take off, we need to start monitoring our progress based on the plan that we made previously. We need to do this at regular intervals, at least every hour. We need to record them physically, not just check the fuel and go, yeah, it's all good. And we need to make sure we check the remaining fuel on board to make sure that we have enough so that when we arrive at our destination, we still have our alternate and final reserve fuel intact. If the predicted fuel on arrival is going to be below this, then we can either divert en route to refuel, or in exceptional circumstances, we can commit to an airport. You wouldn't want to commit lightly though. If the weather isn't great, for example, you wouldn't do it. If there's only one runway, it might not be a good idea because the runway could become blocked or damaged, and then you'd be into a mayday situation where you're starting to eat into your final reserve fuel, and also you don't have enough fuel to go to another airport whilst keeping your final reserve. So you've got to think quite hard before you commit to an airport. Using the flight plan to monitor in flight is pretty straightforward work really, because you should have done most of the work on the ground already. You would have a list of waypoints, maybe with predicted levels that you should be at, how long in between each waypoint, the distance, your true airspeed, ground speed, your required fuel and your predicted fuel burn. So what you would do is when you take off, you'll make a note of the time and then give a prediction for your time overhead each waypoint. Let's say we took off at 1500. That means at our first waypoint we'd reach at 1514, then it would be 25, then it would be 40 and 51, for example. Then when you reach a waypoint, you will note down the actual time that you arrived there and the fuel on board. So we made this first time perfectly at roughly 3, and we had 4,500 kilograms left on board. So we know that we're actually up in fuel. This is a good situation. We can carry on happily and not have to worry about our fuel here. If, say for instance, we got to the next waypoint and we only had 3,500 kilograms, but we required 3,800 kilograms, this could indicate something has changed from the flight plan. This could be down to a number of factors, such as maybe a long taxi out, a step climb, which delays the time that we reach our cruise altitude and we burn more fuel at lower levels. Could be something like a longer routing by air traffic control. They might have had to deviate us off this flight plan and then rejoin it. Could be a fuel leak, could be a stronger headwind, indicated maybe by a late arrival at this next waypoint. Say we arrived here at 30, that would mean we're not going as fast, or maybe we've had to take this diversion that air traffic control have put us on. If you can justify the reason your fuel is lower, and it's a reasonable number, then you can safely say there's no fuel leak, which is of course a bit of an emergency situation. You need to sort that out, try and land if that is the case. If you get to the situation where you arrive at a waypoint and your fuel level is lower than you want, then there's a few things you can do to save fuel, such as climbing or descending into less strong headwinds or stronger tailwinds. You could also request shortcuts from air traffic control, request a higher level for more efficient cruise, or request a more favorable approach and runway at your destination so that you maybe not flying a whole looping arrival procedure in towards an airport. But these might be a bit tricky to coordinate, because generally there'll be an arrival for your direction and the airport that you're going to for the runway that is in use. On the ground, we will have most likely calculated our optimal descent point, and this is usually displayed on a jet aircraft on something called our ND, our navigation display. We know that we should be prepared for our approach and landing by that point with the correct amount of fuel on board to safely do that arrival approach, landing, potentially go around, divert, whilst maintaining that final reserve fuel. Often though, air traffic control will ask us to descend early or hold off our descent so that we go down at a non-optimal point. We may also be given some requirements for the descent by air traffic control. Say we are at flight level 300 and air traffic control say descend to flight level 250 to be level 20 nautical miles before waypoint Wallet. Let's say we're 50 nautical miles from Wallet, traveling at a ground speed of 270 knots. We would need to calculate, therefore, a vertical speed in order to do this. In reality, you would just start the descent at a reasonable rate and adjust as required whilst doing the calculations in your head, so that you're at least making progress towards this goal while you figure out the optimal vertical speed to reach this level by this point. So in this example, we have 5,000 feet to cover vertically, 300 to 250, and we have 30 nautical miles to do it because we need to do it by this point here. So doing some simple speed distance time calculations, we can find a time that it takes to cover this distance, and that time will be the same that we need to cover this distance. So our speed 270, our distance of 30 gives us our time, and if you do that calculation, it works out at just under 7 minutes. So let's just call it 7 minutes. We then need to cover 5,000 feet vertically in 7 minutes. So our speed distance time for that gives us an answer of 714 feet per minute. Make sure you've got all the units correct. You might have to convert from hours to minutes, from feet to nautical miles and all that kind of stuff. So just make sure you're using the correct units. Say we started our descent going down at 500 feet per minute while working out this calculation. Then we could set a higher rate than the 714 feet per minute needed to catch up with the nice steady descent rate, and then adjust and refine as we go down. And it's often easier to think of these descents in the terms of big round numbers. I would look at that and go, right, we'll be there in about 7 minutes. If I do 1,000 feet per minute, then that will be 7,000 feet of descent. I only need 5. So if I do maybe 500 feet per minute in 7 minutes, that's only going to be 3,500. So it's going to be somewhere between 1,000 feet per minute and 500 feet per minute, probably favoring the 1,000 feet per minute number, because that's on the safer side. We might reach level 250 by 30 nautical miles before wallet, or 25 or something like that. But it's better to be that way around than to be late in your descent. And it's easier to use these round numbers because, remember, you're going to be doing the calculations in your head while flying, talking to air traffic control and thinking ahead to the next thing you need to be doing. So simplicity is key for in-flight calculations. And as well as for descent planning, the same calculations could be used for any en route level changes or descents or climbs that are required or asked of you by air traffic control. As well as asking for adjustments to your level, air traffic control might also ask you to adjust your speed, which will alter your time overhead certain waypoints. You need to be accurate with your time overhead waypoints in certain situations and predictions of your ETA, your estimated time of arrival. Say, for instance, an airport was closing at midnight. You would like to know ahead of time if you're going to make it or if you're going to need to speed up in order to get there. Let's say we're due to arrive at an airport at 23:58, just before closing time at midnight. With 320 nautical miles to go, air traffic control asks us to reduce our speed from Mach 0.79 to Mach 0.73. We have a temperature of minus 58 degrees and a wind component of an 80 knot tailwind. So the question is, can we accept the speed reduction and still make it home in time? We'll basically need to calculate the ground speed change and calculate a new estimated time of arrival. So currently we have a speed of Mach 0.79, which is our ratio of our true airspeed to our local speed of sound. So 0.79 equals our true airspeed over the local speed of sound. Local speed of sound is 39 times the square root of the absolute temperature. So 273 minus 58 in this case gives us 215. And then we calculate our true airspeed from that. If you pop that into a calculator, you'll get something in the region of around 452 knots. Remember, we've got the 80 knot tailwind, so that's going to give us a ground speed which is equal to 532 knots. With 320 nautical miles to go at that ground speed, that means it'll take us 36 minutes to cover this distance. And that therefore means that air traffic control made this request of us at 23:22. 23:22, 36 minutes, we're supposed to arrive at 23:58. Then we calculate a new ground speed, add it onto this, and that'll give us our new ETA. So we have the same local speed of sound, but we're doing Mach 0.73 instead of Mach 0.79. So if we pop that into a calculator, you'll get a true airspeed of 417 knots plus the 80 knot tailwind, and we get 497 knots. And then you're just doing speed, distance, time. 497 knots equals the distance, 320 over the time, making our time 39 minutes. With that 39 minutes, we add it on to 23:22 and we get a new arrival time of 1 minute past midnight. So we couldn't accept this slowdown if we wanted to make it home before the airport closes. In reality, air traffic control aren't that mean. They would probably let you in if you were 1 minute late. But you do have to know about speed and therefore time adjustments to create an accurate estimated time of arrival. This might seem like a lot of work to be doing in the air, but in a jet you have a flight management computer that you can put all this data into, and it will calculate the new estimated time of arrival based off of the new Mach number and any wind data that you've put into it. Contingency fuel is carried to cover us for any unforeseen circumstances, and it is usually 5% of the trip fuel, or it can be modified with certain procedures such as the 3% en route alternate procedure. This is an example of a contingency plan. It's a pretty basic one, but it's some more fuel that we have on board to help us in the case that we deviate from the flight plan and do something a bit different. There's a couple more complicated contingency plans that are useful to use when flying that can help you make an appropriate decision should the situation arise. The first we're going to look at is the point of equal time procedure, which you would use for making a continue or a return decision. It is faster to turn around and head back sometimes than it is to continue on to the destination airport, and it can be used, this point of equal time, can be used as a final line in the sand where we know if we go past it, it's better just to continue than it is to divert if anything happens, maybe somebody's having a heart attack on board or an engine fails, these kind of things. So the most useful case for this is when you're flying over something like the ocean. It's a long way in between airports, so you want to know if it's better to turn around or continue on. And if we're flying from A to B in still air conditions, the point of equal time is simply halfway along the route. It's going to take the same amount of time to fly back as it is to carry on. But it's never no wind conditions. There's always a bit of wind to consider. That means we have to consider the ground speed in one direction and the ground speed in the other. And luckily there's a nice formula that we can use for this. So basically what we want is the time to go home to equal the time to continue on. Then we just substitute in some speed, distance, time calculations pretty much and do a bit of rearranging. So the time home is going to equal our distance to the point of equal time. So this distance in here, we'll call this P, divided by the ground speed, and that's going to be the ground speed that it's going to take to go home. So if we go ground speed home, we'll just give that an H. We want that to equal the total distance, we'll call that D, minus the distance it takes to get to this, which gives us our remaining distance, and we want to divide that by the ground speed that it's going to be to fly onwards, GSO. So we'll just give that a little O. Then we do some rearranging, so we get something that looks like this. P times O equals H times D minus P. Expanding that out, P times O equals HD minus HP. We can then take the H over to this side and we get PO plus HP equals HD. We want to get the P on its own, so we take the P out, O plus H equals HD, and then we can divide HD by O plus H. Some algebra for you. Just if you don't know how to rearrange, you're not happy with that, just remember this formula. H times D over O plus H. So if we were to put it into an example, let's say we had a total distance of 400 nautical miles. Our true airspeed is going to be 190 knots with a 40 knot headwind. So what would be the distance and time to our point of equal time P? So we're just going to simply put in some numbers. We want to find P. Our H, which is our homeward bound ground speed, is going to be 190 knots, turned around plus 40 knots, so it's going to be 230 knots. Our total distance, 400 nautical miles, divided by our ground speed going onwards, 190 minus 40, 150 plus the speed to go back, which is 230. And if you calculate all that, you'll get a distance of 242 nautical miles. And then if you wanted to find out the time, just a nice speed distance time calculation will get you a time of 1 hour 37 mins. So our point of equal time here is 242 nautical miles, which is 1 hour 37 into our flight. So we know that up to that point, it's best to turn back towards airport A, and past this point, it's better and quicker to go onwards to B. This means that we have a plan in place already, so that if anything happens ahead of time, we know what decision we're going to make. Somebody has a heart attack here, we're turning around. Somebody has a heart attack here, we're carrying on. It just takes a bit of work out so that you're not making a decision in your head whilst trying to deal with whatever situation is on board. The point of safe return procedure is a contingency procedure that was used for isolated aeroports, for example, St. Helena in the mid-Atlantic, or maybe flights to the South Pole where there's not any suitable destination alternates or en route alternates really, and therefore you need to be sure that you can make an approach and land at the isolated airport, because there won't be sufficient fuel to do an approach, go around and return to the departure airport with final reserves still intact. This means that there's a certain point en route that you need to decide, your point of safe return, that you need to decide to continue or return. So it's quite similar to the point of equal time, but it's more to do with your fuel levels and your endurance of the aircraft. So let's consider our departure from destination A and B again, and we would have a total endurance for the plane, which will be a measure of time and how long the aircraft can actually stay in the air. This means that we need to figure out a time or location along our route where we have a suitable endurance to return to our destination. It's basically going to be half our endurance, because we're going to fly half the endurance out to this point and the other half will be used to turn around and fly us back. We're splitting the total endurance into an out and back leg. This means that in terms of distance to the point of safe return, we need to be equal in terms of out and back in terms of nautical air miles. This means that our ground speed out, O, times a time to the PSR, the point of safe return, has to equal our ground speed times time home. So we'll go H times T here. O for out ground speed, H for home ground speed. And we also need to make sure that that is lower than the total endurance of our aircraft. So we also need to, I've done this the wrong way around, so let's call this H times E for our total endurance, and we need to take off the H times T number. So it's basically working out, can we make it back with still having the endurance intact? And this is going to work out distances. So rearranging, OT plus HT equals HE. We kind of want the time on its own, so we're going to remove time from this and bring out O plus H equals HE, and then time is on its own, HE over O plus H. Bit of rearranging, hopefully it makes sense. Just remember this formula, basically, is what I want you to get from this. So to give an example, let's say we had a total distance here of 12,000 nautical miles. We had a safe endurance of 6 hours with a ground speed of 550 knots on the outward leg, and it's going to be 500 on the way back. We then just plug in the numbers. So the time is going to be home speed, 500 times 6, over our outspeed plus H. So our outspeed 500 plus 550, 1050. Time of our point of safe return is going to be 2.86 hours, which is 2 hours and 51 minutes. And then using speed, distance, time calculations, we'd use our outbound speed. It's going to be a distance of 1571 nautical miles along the route. So I realised whilst editing the video there that my numbers were a bit crap for that example. So the point of safe return is obviously more than the total distance of the route. Basically that means that anywhere along that route it's safe to return. It's going to take us less than 3 hours to get all the way to the destination, and obviously less than 3 hours to get back. Something you might have to consider is if fuel flow is different in both directions, which is pretty likely because you'll be flying at different cruising levels for one direction versus the other, and this can influence the point of safe return. For the formula for this case is still pretty straightforward. Fuel consumption is measured in kilograms per hour. how much fuel you're burning per hour. It's going to be equal to your fuel flow, which is your kilograms per hour, times your ground speed, which is obviously your nautical miles per hour. Your fuel consumption, sorry, is per nautical mile. So let's scratch that. Kilograms per nautical mile. You want to know how much fuel you're burning for every nautical mile of distance, which is going to be however much fuel you're burning per hour times your ground speed, which is your distance per hour. That's a bit messy. But basically what it does is you want to find a point in terms of distance, divide the fuel on board by the consumption out and back, and that means you'll be able to calculate a point of safe return, and a time can be found from that too. So the formula to remember, point of safe return, is your fuel available. Remember, that'll be your fuel minus your final reserve fuel. You want to have that in the bank, otherwise it's a Mayday emergency situation, divided by your consumption out plus your consumption home. We're considering both fuel consumptions, so the total fuel consumption is higher, which will reduce our distance down to a safe point where we can fly out and back. It's quite simple but effective despite my confusion up the top. So just like the point of equal time, this gives us a plan ahead of time so that when it comes to this point of safe return, we need to make a decision based off of very defined factors. Will the airport's weather be good enough for us to land? Yes, let's continue. No, or it's marginal, we would go home. These contingency procedures are very useful for getting ahead of the aircraft and making a plan that can then be actioned if and when it's needed, with time to prepare it and think about how to execute the diversion home or how to continue on to our destination at this isolated island in the middle of the sea.